In this video, I am studying the same problem that I solved in our previous video on finding the frictional force exerted by the walls of a pipe, but this time I'm using the linear momentum conservation law for well-defined inlets and outlets. Now, to study the linear momentum conservation law with well-defined inlets and outlets, I remind you that instead of having an integral here, we put a sum over the inlets and outlets that we have in our control volume. Now, because this sum contains no integral, our velocity will be basically the average velocity. And we said that this is essentially a very big approximation. So in order to account for this big approximation, because of course you can see here, for example, I have this fully developed profile where obviously taking the average value of this velocity removes a lot of the real effect of this velocity variation. So to account for this big approximation, we add this correction factor beta here. This is the linear momentum correction factor. So basically to use this form of the equation, we will have to find the average velocity, first of all, from the profile that is given to us. So I remind you, our profile is given by this expression in this problem. And two, we will have to find the correction factor. So we are going to start first by finding the correction factor beta 2 across our outlet, at which the velocity is non-uniform. It actually shows a fully developed profile. So we want to find this beta 2, which is the linear momentum correction factor across our outlet. We do not study a correction factor across our inlet, mainly because here the velocity is actually uniform, so there is no approximation in our value for the inlet. So basically at our inlet here, we will not have any beta. On our outlet here, we'll just have beta across point 2. So we'll have beta 2 that we need to find. Whereas here, I will not put a correction factor. And the average value will actually just be u1 itself because we have a uniform velocity. Now, to find beta, our formula tells us that beta is equal to 1 over a integral of u squared, where u is the component of the velocity that is across the direction of n, which is normal to our area, over v average squared, which is the approximation that we have taken here in our momentum equation, times dA. So we're integrating over dA. And like I said, this value u is basically just the component of the velocity that is perpendicular to our cross-sectional area. In that situation, the component that is perpendicular to the cross-sectional area is the horizontal component, which is u. So I need to solve this integral. Now, we're trying to find beta 2, which will be an integral of u2, which is given by this equation. The area is the same everywhere, so I will not label it as a2. And v average is, of course, the average value of this profile. And we need to find this one as well in order to be able to solve this integral. So to solve this integral, the area is easy to find. This is just 1 over pi r squared. And I will integrate over u2 squared, which will be u max squared into 1 minus r squared over capital R squared, all squared. This is over dA. Now, because I have this circular pipe, then my infinitesimal area can be just a ring. This is an infinitesimally thin ring of radius r extending from 0 to capital R and of thickness dr, which gives us the area of this infinitesimal ring to be 2 pi r dr. So I can just substitute this right here. Instead of dA, I will have 2 pi r dr, which is the area of the infinitesimal ring, which I will use to integrate over the whole cross-sectional area of the pipe. So basically my integral is over this small r, which is shown here. U max is a constant, so I can take it outside. I'll have U max squared, and I'll also take 2 pi to the outside. And I have pi r squared down here. So I'm left with an integral of 1 minus r squared over capital R squared r dr. Now I have to divide here by v average. However, I left this empty because I'm really not sure of the value of v average. Now, you might be familiar with a fully developed velocity profile, and you might already know that for this fully developed profile, u maximum is equal to twice u average, and u average is going to just show up to be the value of u1 that we have here. And you might be already familiar that beta for this fully developed steady flow should look like this. It will have a value of 4 over 3. But these, if they are not given to you in a problem, you have to derive them as I am doing here, because the question was to find beta 2 by solving the integral. To find now the average value, if you aren't already familiar with the fully developed profile, you will have to find the average value by actually integrating over your velocity profile to find its average. For our velocity profile, we can find u average, which is simply found by 1 over a integral of the velocity that we have over dA. this is 1 over pi capital R squared, integral of u max into 1 minus r squared over capital R squared, and dA again is just 2 pi r dr. We take our constants to the outside. I have u max 2 pi over pi capital R squared, and we integrate over 1 minus r squared over capital R squared times r dr. This will give me u max times 2 over capital R squared, integral of r minus r cubed over r squared dr. This integral goes from 0 to capital R. I will obtain 2u max over capital R squared. R here will be r squared over 2 minus r cubed here will be r power 4. From 0 to capital R, this will be capital R power 4 over 4r squared. So we'll obtain 2u max over r squared into, so I have here half minus quarter, so this is basically r squared over 4. And we end up with this equation, u max over 2. We just found that our u average is just the maximum divided by 2. So I can just substitute this here. I'll have here, instead of u average, u max divided by 2 all squared, which will give me here u max squared over 4. So I'm not going to go over the math of the integral again because this is very similar to when we were finding u average. But basically, when you solve for the integral, you will obtain the following final expression, which resolves into 8 over 6, which is basically 4 over 3. This is our value of beta 2 across the outlet. And this actually applies to any fully developed velocity profile that is for a steady laminar flow. If we have a turbulent flow, like we said before, depending on our Reynolds number, which determines how much turbulence we have, beta usually ranges between 1.01 and 1.03. Now, after finding beta and solving the integral to obtain the value of beta 2 across our outlet to be 4 over 3, we can now proceed to use the momentum law for well-defined inlets and outlets and try to find the friction force using this equation. So again, just as before, I am projecting along the x direction. So I will solve this conservation law, which contains vector quantities along the x-axis in order to resolve these vectors into their x components only and be able to have some scalar quantities. Again, as we did in the previous video, the gravity force has no x components. The pressure forces, they are horizontal. We said that, namely, at the inlet, we have the following pressure force, whereas at the outlet, I have the following pressure force. Of course, by the way, I expect at the outlet the pressure force to be not necessarily greater than the pressure force at the inlet. So this is how our pressure forces look like. And like we said in the previous video, then the pressure force at the inlet will be written to be positive, whereas the pressure force at the outlet is written to be negative. So this is because it's pointing to the left, which is along the negative x-axis. So these actually will resolve to P1 minus P2 times A. I have the same area, so A1 is equal to A2. The cross-sectional area of my pipe is still the same because my pipe did not really converge or diverge across the flow. For the viscous forces, I have the friction, which is the quantity of interest. And like we said, this is opposing the flow direction, so it will point to the left. So I will have minus F for my viscous forces. I have no other forces. My flow is steady, so I will not have any derivations with respect to time. And across my outlet, I will only have one outlet, which is at point 2 here, so I will get beta 2 m dot times my velocity along the x-axis is written as u2, and here I use the average quantities for my well-defined inlets and outlets, and I account for the variation of the actual velocity profile by using the correction factor beta 2, which I just found. For my inlet, I will have no correction factor because at my inlet the velocity is constant, so the average is the velocity itself, and here I will have m dot times u1. Now there is something to notice here. I have used the same flow rate at the inlet and at the outlet. Why? I have one inlet and one outlet and a steady flow. And like we have discussed in our previous chapters, this means that the flow rate at the inlet and the outlet is the same, and I can write this as m dot. Now to find this flow rate, because it's not really given to us in the problem, we can try to find it in terms of the volume flow rate, which is equal to the area times the velocity, whether it's at the inlet or at the outlet. So I can either use A1 U1 or A2